Start recording. So we've covered immediate energy systems. We spent covered like 4 slides on Monday. I realized this morning when I was looking at things talking about glycolysis. Okay. Today we're going to get into kind of what happens at the end of glycolysis, or kind of what happens, what's the fate of pyruvate. Okay. What the Avengers movie, the fate of the world rests upon what happens to pyruvate. Okay. So I'm going to say something to you all that I have written on the board here, and I know it's technically not correct. And I want you all to know that it's technically not correct, but it's likely how you guys have been taught this beforehand. So I will try to explain it to you in this way in the hopes that it will make sense. We're going to do a couple of analogies and then we'll move on to the anaerobic pathways. Okay. So in the Meyerhoff pathways, we go from glucose to pyruvate. Okay. Glucose goes in, pyruvate comes out. Y'all better freaking know that. Okay. If that glucose comes from the bloodstream, we make 2 ATP and reduce 2 molecules of NADH. If that glucose comes from muscle glycogen, 3 ATP. Okay, pretty simple. That part of everything always happens. That's always going on, no matter what is happening in your body. Okay. What happens after that, though, is one of the key determinants of exercise performance and metabolic function, and one of the complicated things that goes on in our bodies. And that is, does pyruvate at the end of the Embden-Meyerhoff pathways become lactic acid, or does it get moved into a mitochondria, okay, and broken down in the Krebs cycle to send more electrons to the electron transport chain, so we can make not just 2 or 3 ATP, but I don't know, whatever we've decided it is this week. They change it like every other week, right? It's like 36 or 39 or 41, or we change our mind. But it's a ton, okay? A huge amount of ATP. And so traditionally, if you look in sort of undergraduate textbooks, they have referred to this idea of pyruvate goes to lactate or lactic acid. Those of you that have forgotten your chemistry or blocked it out because of PTSD, when you take an acid and you put it in water, what happens? Anybody remember? You're like, no, Dr. Black, it's Wednesday, it's the week before spring break. Don't make me fucking do chemistry, right? I've taken chemistry, I don't want to be in chemistry. You put an acid in water, which guess what your cytoplasm is? Mostly water. Guess what your blood is? Mostly water. Okay. Acid in water, it does something called dissociate. Okay. The hydrogen that makes it acidic breaks off. So we convert, it's actually not even pyruvate, it's pyruvic acid, but you convert pyruvate into lactic acid, but we'll talk about it as lactate. Okay. You make lactic acid, the hydrogen comes off, we get lactate, and we get an increase in acidity wherever that was made. This has been called anaerobic glycolysis. Okay. If you look in a lot of textbooks, it's called anaerobic glycolysis. This is a misnomer because all of glycolysis is anaerobic, right? What this is really referring to is an anaerobic phase of pyruvate. Okay, an anaerobic phase. There's an enzyme you need to know. It's called lactate dehydrogenase. When it comes into contact with pyruvate, it makes it into lactic acid. Okay. As a part of that process, though, the NADH that we made in the Embden-Meyerhoff pathways gives its electrons back. By giving the electrons back, it frees up that NADH molecule. It turns it back into NAD, so that the Embden-Meyerhoff pathways can continue. Okay. So that's the good part of this. We make some energy, we recycle our electrons, so NAD can move back up and continue everything and keep glycolysis going. The problem is you make lactic acid, you get hydrogen, you become acidic, everything shuts down in about 30 seconds to 90 seconds. Okay? Your muscles burn, everything gets messed up. The other thing that often happens, and in some ways is preferable, is pyruvate moves into the mitochondria, okay? And we will lose a carbon. Pyruvate has 3 carbons. We lose a carbon as, you guys know what we start peeling carbons off of things in metabolism and they get converted to one thing. It's one of the things that we measure when you're breathing. CO2. Okay? We pull a carbon off, we make CO2, we get an acetyl group, we hook it on to something called coenzyme A, which no one knows what the hell it is, but you hook it on to coenzyme A, it goes into the Krebs cycle, it gets turned into citrate, and then we spin through the Krebs cycle, we make some ATP, and we reduce a huge amount of electron carriers. Okay? This is an aerobic fate of pyruvate. Okay? An aerobic fate. This reaction is driven by an enzyme called PDH, pyruvate dehydrogenase. Okay, PDH. So, when we need lots of energy, when we need things, we need to decide where the pyruvate goes. Okay, and there's this tug of war or this battle in some ways between LDH and PDH to try to figure out, are we going to convert into lactic acid or are we going to go into the mitochondria? Okay, we'll talk a little bit more about that in the coming slides, but this is the big deal. So I'm going to talk about aerobic metabolism very, very briefly, and then we'll talk about how we control these things and kind of the real take home from this. Okay. Okay. So we talked about NADH and how we make that, right? This is showing, as I said, it's actually pyruvic acid, but you've got pyruvate. It comes into contact with LDH. We donate both the hydrogens and the electrons back, and it makes lactic acid. Okay. This same thing happens in the electron transport chain, but we need this so that glycolysis is able to continue. So it's not bad to make some lactic acid. I don't want you guys to get that impression. Okay. It's not bad. You make lots of lactic acid, that's okay. You stop exercising, all that lactate gets dumped into the Krebs cycle and it just gets broken down like normal, right? There's plenty of organisms that function only on lactate. So lactate itself is not the problem. It's really the hydrogen, okay? And so part of this is good, other parts can lead to some bad things, okay? I want to introduce a concept here, okay? A concept. There will be an exercise intensity, okay? There'll be an exercise intensity. It's likely not going to be walking for most of y'all. It's barely walking for me. It's kind of walking fast because I'm out of shape. But there's a tipping point. You guys know about these ideas, these concepts of tipping points, and these kinds of things like a seesaw, right? So you're sitting here right now, predominantly most of your pyruvate is going into aerobic metabolism. Some is getting made to lactic acid, mostly aerobic metabolism, right? You need more energy, you start exercising, you contract your muscles, and we start ramping up, right? Both how much goes into aerobic, but also how much lactic acid we're going to do. At some point, at some exercise intensity, we need enough energy that the amount of lactic acid that we are going to make is going to tip, okay? And it's going to exceed our ability to sort of put the lactate back into the Krebs cycle and do some things. And so we will see a measurable increase in lactate in your blood, okay? In lactate in your blood. Running, I do a little finger stick, I get a drop of blood, I put it into a little analyzer, and I say, okay, you doubled the amount of lactate that's in your blood. This is called a lactate threshold. Okay, it's a threshold work rate, a threshold exercise intensity, and it's the threshold where lactate increases above resting levels. This is an unbelievably important marker physiologically of one, how well your metabolism works, but also of sort of that exercise intensity relative to how well your metabolism works. Once you exceed lactate threshold, your hydrogen ion accumulation is going to continue to go up. And you can work out above lactate threshold a little bit, but you can't go very far above it or you will inexorably fatigue. Okay. And so this is a key kind of parameter. We'll talk about this in relation to VO2 max and stuff on Monday, but this is a very, very sort of key idea and key thing. Okay. Here's an example. Okay. Here's an example. This is a measure from a finger stick of how much lactate is in your blood. Y'all are sitting here, you're resting and do a finger stick. You guys have probably 1 to 2 millimoles of lactate on average at rest in your blood. We put you on an exercise bike, okay, and you start riding. You're at 30 watts, 50 watts, 100 watts. This person up to 200 watts on the bike. They're pretty fit, okay? You're exercising and there's no increase in blood lactate. Metabolism is increasing. Energy demand is increasing, but your blood lactate is not going up, okay? This tells us that your aerobic metabolism is mostly able to provide this ATP. But right here, there's a threshold power output where the amount of ATP I need to sustain this amount of work tips over and I start getting this increase in lactate in my blood, which is suggestive that anaerobic metabolism or pyruvate going to lactic acid is beginning to ramp up, which is suggestive that aerobic metabolism is being sort of taxed to a greater extent. We cannot put all of our pyruvate into the mitochondria, so this begins to happen. Most of us can exercise to about right here or so, and you can keep that pace. You can go at that pace for 15 minutes, 20 minutes, half an hour, maybe 90 minutes if you're pretty well fit. You get out here though, lactate rises into this 6, 7, 8 millimole range. You're going to fatigue within 30 seconds to a minute. Okay. So this is a really important parameter that we can measure to try to understand how well does your metabolism function and then what work rates is that going to allow you to be able to exercise without there being this fatigue. Okay. People that have a lactate threshold at a higher power output are likely more fit. They have better aerobic metabolism. Also, they can run or bike faster or at higher power outputs for longer periods of time. So it's a very, very key measure of aerobic metabolic function and aerobic fitness. So this balance, this tipping point of when does most of the pyruvate or more of the pyruvate begin to get turned into lactic acid versus going into the mitochondria tells us something about your underlying physiology. Okay. Okay. We've talked about lactate accumulation. So I'm going to mention this, but you don't have to know more than just the very, very basics of what this is. This is in some ways probably graduate or master's level exercise physiology. Okay. There is a phenomenon that we call the lactate shuttle. Okay. You make lactate. Pyruvate is turned into lactic acid. It dissociates. That lactate is just a carbon molecule, just like pyruvate, just like glucose. Okay. And we actually use it as an energy source. And what happens is you make it in some muscle fibers, and then we shuttle it. We move it from one muscle fiber into an adjacent fiber. Or it goes into the blood and it moves from your quads and gets taken up by your bicep or by your brain or something in that particular way. And that's called the lactate shuttle. Okay? The lactate shuttle. It is driven by something called a monocarboxylase transferase. It's MCT1 and MCT4. You do not have to know this. You do not have to know that. It's just an enzyme and it helps us transfer these things. The better you are at shuttling, the higher your lactate threshold is. Okay? Slow twitch fibers are better at shuttling than fast twitch fibers. Slow twitch fibers have a less active lactate dehydrogenase in them. They have more mitochondria. Slow twitch fibers make less lactate than fast twitch fibers. This is one of the reasons that having slow twitch fibers potentially makes you a better aerobic athlete. Okay, so don't worry about all of the intricacies. I just want you to understand the concept that lactate can be shuttled. Okay. Okay. Now, let's cover the aerobic pathways. They're relatively straightforward. I know you guys have seen these things like 18 times, right? So we are going to cover this essentially in 3 steps. Okay, essentially in 3 steps. The first step is sort of a transition step. Okay, you see I have pyruvate at the top. Okay, that pyruvate has come out of the Embden-Meyerhoff pathways, out of glycolysis. Okay, we are then going to transition pyruvate into acetyl coenzyme A, which will allow that pyruvate or that acetyl group to then move into the Krebs. As part of that transition step, note that CO2 comes off, we make carbon dioxide, and we grab some electrons that we're going to end up in the electron transport chain. Okay. So the transition step yields us pyruvate to acetyl-CoA. It yields us carbon dioxide, which is why when we start exercising, we're going to breathe off more CO2 and we store some electrons. That acetyl group gets transferred onto a molecule called oxaloacetate. That's a 4-carbon molecule. Acetyl groups, right? We're in organic chemistry, acetyl 2 carbons, okay? That makes something called citrate that has 6 carbons. I know it seems weird, right? We started with glucose, it had 6, we're now back to 6. I don't really understand, right? The world has gone crazy on us. But citrate, this is where this used to be called the citric acid cycle. It's now called the Krebs cycle. You have citrate, and then things spin around. Okay. You do not have to know steps. You do not have to know the enzymes. You don't even have to know how much ATP or how many molecules of NADH and FADH that we reduce. Okay. You can all Google. You can look it up. You can all get on ChatGPT. Look it up, okay? What I want you to understand about this is that it's a multi-step process, which makes it slow, okay? Pyruvate goes in as acetyl-CoA, and basically nothing comes out. Or what comes out is carbon dioxide, a little bit of ATP, and a bunch of electrons. Okay, we've stored a bunch of electrons on NADH and FADH. And we're going to use all of those in the next step. And that's the important thing to know and understand. Okay? If you want to get into the intricacies of all of this and how and why it works, and you want to know all the enzymes and those things, great. Take biochemistry. Okay? Take biochemistry. I will tell you this enzyme here. And I will, this is only because this was an important thing in a quiz bowl one time. Alpha ketoglutarate dehydrogenase is the rate limiting enzyme of the Krebs cycle. That's the slowest step. I took a group many years ago to a national quiz bowl competition because we won a regional one as part of our big national conference for the American College of Sports Medicine. We were winning, it's known as Jeopardy. We were winning going into Final Jeopardy, and that was the Final Jeopardy question. What is the rate limiting enzyme in the Krebs cycle? And Dr. Mike, who was teaching exercise phys at the time, did not teach that. He didn't know all the other things about the Krebs cycle, but not the rate limiting enzyme. Right, and that was the thing. So I was mentioning, I'm not going to ask you about it, mostly because this is not the thing. This is fast enough. Krebs is mostly limited by how fast the electron transport chain can return the NAD molecules back to it. Okay, but that's what happens in the Krebs cycle. We get carbon dioxide, we get a lot of electrons, but it's slow. And that's going to become important in a few minutes, okay? All right, so I was showing those kinds of things. Let me show you then the electron transport chain. The Krebs cycle is taking place inside, in the very center of a mitochondria, okay? In the very center in the matrix. Okay? the electron transport chain is a series of molecules that are going to be sort of placed into the inner membrane of the mitochondria. So here's the outside, the outer membrane, here's the inner membrane, and put in that inner membrane are these molecules that you see here in purple that are called cytochromes. Cytochromes have iron in them, so they're very, very positively charged. Because of that, they very much want to take the electrons off of NADH and FADH, okay? And those electrons bind to complex 1, they then get shifted to complex 2 and 3 and 4, and so they get passed down this chain. As that happens, the electrons leave NADH. When the electrons move, that leaves a bunch of hydrogen ions. As the electrons move, they create what is in essence a vacuum that pulls all of these hydrogen from the inner part of the mitochondria into the space between the inner and outer membrane that you see up here. Okay? That creates this giant hydrogen concentration gradient, and then we get to the very end, okay, and there's an enzyme called ATP synthase. You need to know that. ATP synthase. And what happens at ATP synthase is it has a channel that lets these hydrogen ions move down their concentration gradient. So they pass from this space between the inner and outer membrane back down into the very inside, into the matrix. As they move, that drives the enzyme, and that enzyme then puts phosphate onto ADP. That's the enzyme that makes the vast majority of the ATP that you use every day in your body. It's all done in the mitochondria. A lot of it is done in the mitochondria. Okay? As those hydrogen pass back in, okay, they are met by an oxygen molecule. The oxygen molecule takes the electrons off of complex 4, binds back to those hydrogens, and we make water. Right? Without oxygen, the electrons cannot get off of complex 4, and the entire process stops. Okay? This is why aerobic metabolism requires oxygen. It is what we call a final electron acceptor. Okay? It's the final piece or step in the electron transport chain. Okay? And so we do all of this and we make a shit ton of ATP. That's the end. Okay? That's the end. 36, 38, 39, whatever we've decided this week it is, they're like, no, for every NADH, you make 2.5 ATP. You cannot make 2.5 ATP. You either make 2 or you make 3, right? Or you make 4. Like you can't make a half of an ATP. And so we just, they keep changing their mind when we get better biochemical techniques. The end is, you're going to make somewhere in the high 30s if you oxidize and you break down a glucose molecule all the way through aerobic metabolism, or you're going to make 2 or 3 if it's done through glycolysis. Okay? So you get a bunch, or you get a little bit. All right? Does that make sense? You guys with me? Okay. Now we come to the hard part. Every semester I try a different analogy with this, and I've not quite landed on one that I think is going to work. Okay, but I like this one. I was thinking about this again on the way in this morning. Okay. We need to try to understand, okay, how and why in some circumstances, that pyruvate will go to lactic acid, and in other circumstances that pyruvate will make it into the Krebs cycle and go this particular direction. Okay? So what I want you guys to think of is, I want you to think of metabolism like a water faucet. Okay, like a water faucet. Right? You guys are aware of a water faucet? You guys know what a bath? You guys, who's taking a bath? Everybody's taking a bath at some point in your life? We take a lot of baths in the Black household. It's mostly just playtime. We get into the bath. You would not believe the number of things they make. We have potions for bath time. We have colors for bath time. We got all kinds of like things that just sing Baby Shark all the damn time. Oh God. Man, let me just tell you.
Sounds like you're going through PTSD, right?
I am. I just like, it's bath time and I just hear Baby Shark for a half minute. So we have like 7 every time my mom and dad come to visit, they buy her a new Baby Shark. We've got Mommy Shark, we've got Daddy Shark, we've got pink Baby Shark, we've got yellow Baby Shark. I don't understand. Okay. Anyway, you're taking a bath, right? Okay. Imagine that, okay? Imagine that metabolism is like a faucet. Glucose moving through metabolism, okay? Glucose moving through metabolism is the water, okay? That's the water coming out of the faucet. When energy demand in your muscles goes up, you open the faucet, right? I need ATP. I gotta start running more of the water, more of the glucose through, okay? Now, the bathtub, in this instance, the bathtub is aerobic metabolism, okay? The bathtub has a certain size. There's a certain amount of water that we can run through into the bathtub and it all fits, right? It also fits, okay? It's a bit of a torture analogy, I'm gonna get it, okay? If we turn the faucet on enough, right? Imagine it's not a faucet, it's like a fire hose shooting water. At some point, the amount of water or glucose moving through is more than the bathtub can handle. And what happens then? When you overfill a bathtub, where does the water go? It seeps out, right? Anybody ever been to a really, really like fancy like swimming pool where they have like actual swimming and diving events? You guys know what they have on the sides? These big drains on the side so that when you get waves and stuff and it washes, it keeps the water really, really flat. Okay? It's like side drains. The side drains, that's glycolysis. Okay? Well, that's making lactic acid. We overflow and then it gets picked up by those side sources. We also only have a certain amount of capacity there for everything that's going to go. So when you need more energy, the first thing that we do, okay, is we start using creatine phosphate, but you guys will see the next slides, is we ramp up glucose moving into this metabolic system. We open the faucet, we start blowing glucose in, okay? It comes from our bloodstream, it comes from muscle glycogen, and then at the end of all of that, it's just how big is your bathtub, and can we basically fill up the bathtub enough to get enough energy, okay? And if not, then we make lactic acid, and eventually that's going to come forward. So, anybody? Y'all are probably too young to appreciate these things. My wife and I bought our first house. Okay, I drove back by and saw our very first house in Athens, Georgia, last weekend. It was the moment we bought our first house. When was that? In the summer of 2007. Ooh, how old? Okay. Bought it in the summer of 2007. We were so excited. We had this giant bathtub, right? It had whirlpool jets, and we're like, we are adults. We have a master bathroom. It has this big bathtub, and there are whirlpool jets in it, and all of these different things. Anybody ever seen one of these? Maybe your parents have one, or y'all live in a house and you got one of these things? You think it's going to be great, and you never use it because by the time you get it full, you're out of hot water. But one of the ways that we can make aerobic metabolism more efficient and run better is to make the bathtub bigger. Okay, you can put more glucose through the system into aerobic metabolism if you have a bigger bathtub. So the bathtub is like mitochondria. If you have more mitochondria, there's a greater chance more pyruvate can manage to go in. and we should handle it in that way. Okay, so I'll explain a few more of these things as we kind of move along. I don't know, y'all, I feel like I've confused y'all more with my bath. I thought I had a good bathtub analogy to make up all this out. May not have worked for me. That's okay. That's okay. All right. So the thing that we need to, and I've just put some things in here. You guys can kind of see where stuff is going on if you care. You don't have to know all of this other kinds of stuff. Okay. I'm going to introduce a little bit of a concept, and then we're going to talk about rate control. Okay. But here's the mitochondria. Glycolysis and the breakdown of glucose is taking place out here in the cytoplasm. Okay. What we would love to be able to do is to put glucose in as acetyl-CoA into the Krebs cycle, and we make ATP through the electron transport chain. Okay. One of the reasons that metabolism is so complicated is that while this is happening, something else is also happening. You are taking fat or lipid, and you're also, through a process called beta oxidation, you're also making acetyl-CoA from the breakdown of fat and putting that acetyl-CoA into the Krebs cycle to make energy through aerobic metabolism as well. So aerobic metabolism uses both carbohydrates in the form of glucose and fat to try to arrive at the same sort of thing. And this is why this gets so complicated, is that the things that regulate carbohydrate metabolism are not the same things that regulate fat metabolism. And yet they're happening simultaneously, and they're going to have some level of interaction with each other. And this is why this is such a complicated process. Okay. The end goal of metabolism is you guys need X amount of energy right now. Just make sure that we make it. We don't care if it comes from fat. We don't care if it comes from food. It's just a matter of where are we getting enough in total. Okay. It's all that we really, really sort of need to understand. Okay. When we use fat for energy, we have to understand how we store fat and where it comes from. Okay. So this is also going to go through aerobic metabolism, but we generally store fat in your body as what we call a triglyceride. Okay. My flabby tricep is just triglyceride. Okay. It's triglyceride. A triglyceride is what we call a free fatty acid. There's 3 of them bound to kind of a structural thing. It's called a glycerol. And what we need to do in order to break down lipid tissue is we have to take our stored triglyceride, go through a process called lipolysis, and break it down into glycerol and our free fatty acids. And those glycerol and free fatty acids move into the bloodstream, into your muscles, and then those things get broken down and put into the mitochondria. Okay? You have triglyceride in all adipose tissue, and you have it in what we call intramuscular triglyceride stores. You have some fat inside your skeletal muscle. There's this giant energy depot. Okay. We also will sometimes store fat as cholesterol. That's mostly from the food, and the cholesterol will get converted into triglycerides. And then we have phospholipids that make up membranes. We don't really do much with these. This is the big thing. Okay. This is the big thing. You go to Chick-fil-A, you get a chicken biscuit in the morning, eat it, and your blood triglyceride levels go up. And what you hope is that you can break those things down and put them into your muscles and use them for energy today. If you get too much of them, then if it floats around in your blood long enough, then those triglycerides will get sort of put into adipose tissue. Okay, that's what we've got. That's this process here. Okay. Now, I am going to sort of run through what this process looks like. You're not responsible for these steps. I just want to show you that it's kind of a complicated process. Okay. You see that I put some numbers on here? This is kind of a pictographic demonstration of the process of using lipids from metabolism. But step 1 is lipolysis. Okay. You haven't eaten enough today, you haven't had breakfast, you activate lipolysis, you start breaking down adipose tissue, your blood triglyceride levels and your blood free fatty acid levels go up. They get at the very top there at 2, they get pulled into the bloodstream. They float around in the bloodstream and then they get pulled into a muscle cell. There's specialized receptors, right? They're going to be up there, FAB-P and the fat CD36 and those things. Doesn't matter. Okay, we pull it from the blood into the muscle. The muscle then moves it down, binds it to coenzyme A, and sticks it into the mitochondria. Once it's in the mitochondria, free fatty acid looks like a molecule of pyruvate or a molecule of glucose. It's just much, much longer. Okay, it's got 14 or 16 carbons instead of 3. And so you move it in, and then you just start peeling off 2 carbons at a time. And you put those acetyl groups into the Krebs cycle, and it goes around and around. Okay? So if it's much bigger and it has more carbons, you can make more energy. Okay? You break down 1 molecule of fat, depending upon what it is, and you might get 85, 90, 100 molecules of ATP, as opposed to say like the 35 to 40 that we get from a molecule. Okay. Now, in the slides, I walk down what happens in every one of the steps that goes through all of this. Y'all are not responsible for that. Okay, you're not responsible. I just want you to know that we store fat in adipose tissue as triglycerides. In the process of lipolysis, we break the triglycerides down. They become free fatty acids in the blood. Those move into muscle, into the mitochondria, and they go in the Krebs. All that I want you guys to know. Okay. The Krebs cycle is very non-discriminatory. If there's fat that's being put in there, great, it's going to use it. If there's carbohydrate that's being put in, great, it's going to use it. It just, all that it cares about is where am I going to get some acetyl to be able to move through the Krebs cycle to make energy. Okay. This is why what you eat matters for what you burn to get energy. If you eat a lot of carbs, guess what you're going to burn the most of? Carbs. If you eat a lot of fat, carnivores, what are you going to burn a lot? Fat. Okay. And so that's where some of these ideas and these kinds of things. Okay. That's kind of where we are. Okay. So let me talk about this one concept, and then we'll get into some regulatory things. Okay. We'll do bro science for a second. Okay. You want to do bro science? This is a very bro. We're going to dispel a bro myth. Okay. All right. Used to, bros didn't run. They probably don't run very much now either, right? Bros don't squat, bros don't run. Okay? Do you guys know how people train for sort of bodybuilding competitions? You know what they do? Pardon? They resistance train. What else do they do? What does their schedule look like? Anybody know? I only noticed I have a bodybuilder that is in my lab today. Yesterday was wearing a weighted vest around because he thinks that it will help to reset. He's trying to cut, basically. So bodybuilders will eat a bunch, work out a bunch, just get big, right? Then, this is super healthy, right? And I'll have a couple of wrestlers in here. Y'all would never have done this, but then they cut. And by cut, they starve themselves. Okay? Get as big as you can, and then starve yourself and try to lose adipose tissue while maintaining muscle mass. So then you look really lean. Then you get a spray tan and take some salt pills. So you look like a football, and then you're ready for your competition, right? You got to look real dry. That's what they call it. You got to look real dry and veiny and everything, right? Lots of definition. Okay, so. Bernie, don't point at people, Bernie. That's not okay. Don't point. Don't single people out. Okay? Anyway, that's how they do things. Okay? one of the things that they used to do when they were trying to cut was walk on the treadmill. Don't run, walk. And the reason that they would walk is illustrated in this particular slide right here. Okay? We know now that that's not the best. I mean, it's fine. You can walk. That's okay. And they would walk like, y'all have seen the people, right? We're going to walk at like a 10% grade. We're walking like lean back like this, doing things. Hey, I'm happy people are doing stuff. Okay? But it's illustrated right here. What this thing shows is the percentage of maximal oxygen consumption. So the percentage of your maximal aerobic metabolism. Okay? So this is walking, jogging fast, really kind of all out. Okay? The ratio that is graphed here is the fat oxidation rate. Okay? What does that graph show? Where is fat oxidation rate highest?
Around like 55%.
Okay? 50, 60%. What happens to fat oxidation rate as you move up to a higher percentage of VO2 max? As you run faster and faster, it starts to go down. Okay? This is a physiological certainty. Okay? The higher the exercise intensity as a percentage of your VO2 max, the less fat as a percentage of total energy you will break down. Okay? As fat goes down, you're getting all of your energy from carbs. Okay? It's a speed issue. Right? There's way more steps that are involved in breaking down fat, which I haven't shown you guys. It's a much slower process than taking glucose, going through glycolysis, and right into the process. Okay? So, why would bodybuilders walk, not run? They were trying to burn extra calories to lose body fat. Why were they walking? Because walking preferentially seems to burn a larger percentage of calories from walking and are going to be burned in fat versus if they were jogging or running pretty fast. Okay? Does anybody see the problem and why you don't need to do this? Okay, it's a good thought. It's not exactly right, but we're getting close. Okay. If I walk for an hour, how far am I going to go?
Roughly 3 miles, because every person walks about 3 miles per hour.
Okay, 3 to 4 miles. Okay. If I walk fast, probably 4. For my wife, a speed walker, probably 4. Okay. If I ran for an hour, even pretty freaking slow, how far am I going to go in an hour?
How slow are we talking?
No. Right? 6, 7, 8 miles, I don't know. Okay. Calorie burn during exercise is related to work, which is related to distance covered. You are going to burn roughly 100 calories per mile. It's not exactly 100, it all depends on lots of things, but roughly 100 calories per mile. Okay? Whether you walk or whether you run, it's still 100 calories. Okay? So if I ran for an hour and I burned 800 calories, but it was 60% carbs and 40% fat, or I walked for an hour and I burned 400 calories and it was 60-40 fat, the math still works to run. Because you burn so many more total calories by going faster that offsets the kind of small sort of shift that we're going to get in sort of fat burning. Okay? Anybody ever here do cardio in the morning and you not have breakfast and you're fasting? Yeah? Okay. One, you feel like shit, it's hard. blood glucose is low, those kinds of things. When you are fasted, this whole thing gets shifted up. Okay? Whole thing gets shifted up. Fasted exercise burns every calorie that is burned, a larger percentage of those calories come from fat than if you had something to eat. Okay? Additionally, the single most terrible thing, and I've done a lot of terrible things in the name of science in my life. Okay? A lot of terrible things. The worst thing that we did was 4 sets of 10 of our 10 RM on squats, leg press, hack squats, knee extensions. Okay? Basically, we crushed the resistance training workout. Then we got on the bike and rode for 90 minutes. If you do resistance training first, you release all of the hormone responses that you get, as you guys will see, that regulate glucose metabolism, also ramp up fat breakdown. So you dump all of this fat into the system. If you do resistance training first, you also shift this thing up. I do not advise this. It was so terrible. It was so bad to do those kinds of things. Okay. Additionally, the longer you exercise, the greater the percentage of your calories come from fat as well. Okay. And so it's about appearance of fat in the bloodstream. It takes a little while. That's what we've got here. Okay. So there's some rhyme and reason to all of this, but it probably doesn't make that much of a difference. If you're trying to lose weight, it's better to exercise than not exercise. It doesn't make that much of an appreciable difference if you want to exercise in the morning when you're fasted versus in the evening or at lunchtime. Really, if you, as we was, we'll see if you want to lose weight, you got to stop going to Chick-fil-A. Right? You just got to not eat so much. It's hard to exercise enough to put yourself in a big enough caloric deficit. Okay, this concept is related to one thing that I do want you to know. Okay, what I'm showing here is the same graph, but we've got fat in kind of this aqua color, and I've got carbs in kind of the blue, kind of purpley blue there. Okay, and so at very low percentages of VO2 max, right? You guys are resting, we're like, it's not going to be quite this. It's more like 60-40 fat to carbohydrates for all of the calories. As this goes up, as intensity goes up, carb use as a percentage increases, fat use begins to fall. There is a point, and it's at a different percentage of max for everyone, but there is a point right here where they cross over, where it's exactly 50-50. This is called the crossover point. Okay, the crossover point. It used to be a much kind of more popular concept. You guys might see it in popular press. You might see it if you poke around on Reddit looking for things and all of this, but this is what is meant by that. It's the place basically at which energy use is exactly 50% carbs and 50% fat. If you're untrained like me, the crossover point is going to occur during walking. If you're very, very highly trained, the crossover point might occur like way out here at 60 or 65%. People that are better aerobically trained derive more of their energy at all times from fat than from carbohydrates. Okay. Aerobic training lets you eat more Doritos, both in an absolute and a relative sense. Okay. You'll get to be my age and you're like, the only reason I want to work out is because I like to eat. I want to eat and I want to sleep. It's all that I really want out of the day. Okay. Okay. All right. Let's try to finish this here by talking about what I'm going to call temporal organization or rate control. Question.
Like supplementing with ketones that
Yes.
help endurance performance or endurance.
Oh God. Okay. So that's a complicated question. The question is, if I supplement with ketones, you guys know what a ketone body is? Right? Your body will, if you do not eat carbohydrates, it will eventually go into what we call ketoacidosis, right? And so you start making these ketone bodies. One of the ways that you can tell if you have a friend who's diabetic that they need some insulin or they're having some problems is they can become ketosis. If you have a friend who's doing bodybuilding competition, they're doing low carb, and you go around them and their breath starts smelling a little fruity, that means they're in ketosis. You can supplement ketone bodies. And when you use the ketone bodies, basically, to not use glucose and not use fat in these things, and will enhance your exercise performance. And it's a complicated question. Sometimes, in some situations, the answer is yes. Doesn't work in everyone. It may work better in people that are highly trained. It may work better in people that are used to or sort of take the ketones kind of over and over again on those kinds of things. There's an idea that you can train your body to use, you can become what we call fat adapted. You can train, you increase mitochondrial numbers, and then you feed yourself more fat, and you can sort of teach your body to rely more on fat. You use more fat, don't use carbs. Using fat does not cause fatigue. You use carbs, you can make lactic acid, you can deplete blood glucose, you can deplete muscle glycogen. All of those things can cause fatigue. So yes, but not in everyone and not in every situation. And probably only in very long endurance, not in kind of short ones. It's a good question. Okay. Time organization. Okay, time organization. This is a way of trying to understand which metabolic pathway is on and which metabolic pathway and therefore which energy substrate is giving us the most energy at any point in time. Okay, at any point in time. So remember, all pathways are active all the time. All substrates, so really carbohydrate and fat, are being broken down in aerobic metabolism all the time. Okay. The pathway that predominates depends upon both overall energy demand. So how much force do we need? How fast are we running? What's the power output on the bike? How much weight are we lifting? That type of thing. Okay. More force, more work, higher ATP needs. Okay. And the speed of the metabolic pathway. Okay. The faster the pathway, the earlier on we're going to use that pathway to provide it. Because there's a hierarchy in the speeds. Okay. There's a hierarchy in the speed. It essentially comes down to supply versus demand. The muscles need ATP to generate force. At that moment that they need the ATP, they do not care where it comes from. They don't care if it comes from the breakdown of creatine phosphate. They don't care if it comes from the formation of lactic acid. They don't care if it comes from fat or carbs in the Krebs cycle. None of that matters. All that matters is I need ATP now. Okay? I need it right now. Give it to me. Okay. So the speed of the pathways is controlled by several enzymes very often. Okay. It has these what we call rate limiting steps. So speed is controlled by a host of different things. And it's that where are those control points? What happens to those control points? Which one is faster or slower than the other that determines which pathway we use at any given point in time. Okay. All right, so we're going to walk through each pathway and talk about their control. We did this once, we will reiterate, okay? The creatine phosphate or the immediate pathways, phosphagen pathways are the fastest. Why are they fastest? They are simple one-step reactions. You reach over and you smack your neighbor on the back of your head. Don't do that. Okay? One-step reaction. Okay? They got the message, they stopped. Okay? Glycolysis is the next fastest. And then oxidative phosphorylation or the aerobic pathways is the third, it's the slowest because it's got to get something through glycolysis or through the breakdown of all of the fat stuff before it can do things. Plus it has its own number of steps. Okay? So because these ones are faster, at the beginning of exercise, we tend to use, regardless of the intensity of activity, we tend to use Creatine phosphate first, glycolysis in conjunction with that, but kind of we switched in from creatine as it begins to dip off to glycolysis and then oxidative phosphorylation if we're doing much more than a walk. Okay? Rate control of creatine phosphate, and this will be true for all of them. The primary thing that stimulates metabolic reactions, that tells all of them to work and speed up, is ADP. Okay? It's ADP. Use ATP in my muscles. I break it down, ADP levels rise. That rise in ADP levels stimulates all of my metabolic pathways to go to work. Okay? So, this is our rate control here. Very simple, one-step reaction, ADP rises, boom, this goes. Typically, we use the creatine phosphate pathway until it's gone. So 10 or 15 seconds. Okay. Glycolysis is a bit more complicated. Glycolysis has sort of 4 enzymes that are going to control this process. Okay. 4 enzymes. Not all of them are actually in glycolysis. Okay. So what goes into glycolysis? What's the starting point in glycolysis? What do we need to start? Glucose. Okay, glucose. One of the primary places that we get glucose is from the breakdown of glycogen in your muscles. Breakdown of muscle glycogen is driven by an enzyme called phosphorylase. Okay, by an enzyme called phosphorylase. If I want to make glycolysis go up, I need to jam more glucose into a cell, and it will drive glycolysis. More coming in. Okay. Several of these enzymes are what we call allosteric. For my chemistry folks, anybody remember what an allosteric enzyme is?
It binds, it's creatine.
It binds things selectively, good. When it binds things, what do those things do to the enzyme? They could be nature, sure. They make it go faster or slower. Okay. Allosteric enzymes are enzymes that you can control. You can speed them up or you can slow them down. So phosphorylase, being allosteric, when phosphorylase gets bound to calcium, or AMP or ADP, or especially if it binds epinephrine and norepinephrine, all of those are things that increase significantly when we begin to increase force production. It turns on phosphorylase, which breaks down glycogen. So the simple act of contracting a muscle leads to glycogen breakdown. So we're going to have more glucose available to go in. So in some instances, phosphorylase can be rate limited. If we don't turn on phosphorylase, we may not have enough glucose to jam into this process, which can slow it down. That's rarely the case, but it does play some role. Okay. The primary rate limiting enzyme in glycolysis, the slowest step, is controlled by PFK, phosphoglucokinase. It's that third step. PFK is also allosteric, and it can be inhibited or slowed down by ATP, creatine phosphate, and hydrogen. Okay? So at rest, when you have large amounts or adequate amounts of ATP, you have adequate amounts of creatine phosphate, you have low levels of hydrogen ions at rest, PFK is largely inhibited, so glycolysis runs pretty slowly. Okay? It is activated by, you guessed it, AMP, ADP, inorganic phosphate, all of things that come from ATP turnover with exercise, and nitrogen, or I guess we should call it this. N4 is it ammonia? Is it urea? I forget. Again, I forgot my organic chemistry.
I think that is ammonia.
I think it's ammonia. So the big thing is it's stimulated by ADP in inorganic phosphate. So at rest, PFK is largely inhibited glycolysis goes slow. During kind of low to moderate exercise intensities, PFK gets turned on and it works as fast as it can. During very, very high intensity exercise though, when you break down a lot of ATP, you break down all of your creatine phosphate, okay? But hydrogen goes up, it inhibits PFK. This is one of the problems with glycolysis. Get end product inhibition. The thing that it makes at the end will eventually turn it off. And that's why you cannot do very, very high intensity exercise where glycolysis is your primary energy source for more than a couple of minutes. Okay? So that's what happens there. That's in the pathway, in the Embden-Meyerhof pathways itself. The last two things are going to kind of be this competing tug of war side of what happens to the pyruvate. Okay? You have LDH and we have PDH. Neither of these are really, I mean, PDH is kind of allosteric. LDH is not particularly allosteric, okay? But LDH comes in different flavors. Fast twitch muscle fibers have a more active LDH inside than slow twitch fibers. So in a fast twitch fiber, for every molecule of pyruvate that you make, more of it gets turned into lactic acid. Okay? And so they're what we call isozymes. There's an H and an M isozyme, or these segments on them. H stands for heart, M stands for muscle. The heart isozyme doesn't work as fast. So slow twitch muscles have two heart variants in it. 2X have two muscles, 2As tend to have an H and an M in there. And so what that is then is now fiber type is controlling LDH. Okay. PDH, on the other hand, is going to drive the pyruvate into acetyl-CoA, going to put it into the Krebs cycle. Right? It gets turned on and activated by ADP and calcium and pyruvate. And it's largely inhibited by large presence of free fatty acids or low glycogen. Okay. So again, it's the same thing. You start to exercise, ADP and calcium ramp up all of our enzyme functions. But it takes it it takes it 30 seconds or a couple of minutes for this to happen. So that's why there's this lag in glycolysis being spread up and PDH getting activated to drive something to the mitochondria. Okay? So it's the combination of function of all of these things that determine how much pyruvate am I going to make coming through glycolysis, and then where is that pyruvate going to go? Okay? Where is it going to go? Those are our primary things that are going to be there. Right? And that's just what I've said. The biggest two things in glycolysis is how much glucose goes in, so how much pyruvate do I make, and then what is my ability to turn that pyruvate into either lactate or into the mitochondria. Glycolysis is the predominant energy pathway when pyruvate formation at the end of the Embden-Meyerhof pathways exceeds the ability of your mitochondria to take that pyruvate in. When you make enough pyruvate that you swamp or put that PDH molecule underwater, and the pyruvate spills over the sides of our bathtub, and then it starts getting made into lactic acid. Okay, or more and more lactic acid. When does this tend to happen? At the onset of exercise, and when you do very high intensity exercise, when the rate of pyruvate formation exceeds the ability of your mitochondria to take it in and use. Okay? So, if I want to make less lactic acid, I need more mitochondria. Or I need to mobilize less glucose through glycolysis. So I need to use more fat in those two ways. And those are both things that are going to happen as you become aerobic. Okay? Does that make sense? This is probably the most conceptually difficult thing we'll do in all of class to me. Okay? Probably the most conceptually difficult. Now, if we look at aerobic metabolism, what's the rate control of aerobic metabolism? So we're going to start at the end. Okay? Electron transport chain is going to be sped up by the presence of ADP. It's going to be inhibited by the presence of ATP. It's mostly controlled by that. Okay? So when you are resting and you've got plenty of ATP, the electron transport chain tends to be relatively inactive. We want to conserve. As you begin to exercise and ATP levels go up, that's gonna get sped up. Okay. Of the two things in aerobic metabolism, the electron transport chain tends to be slower than the Krebs cycle. And so ETC activity generally is the thing that's going to limit how fast the Krebs cycle can work. Okay. As I said, there is a rate limiting enzyme in Krebs, okay, alpha ketoglutarate dehydrogenase, but mostly Krebs is controlled by how quickly we can pull the electrons off of NADH and send the NAD from the transport chain back to the Krebs. Okay. So that's mostly what happens there. So there's only a certain amount of speed that can go on here. Once this reaches its maximal speed, that is going to put a limit in some ways on how much pyruvate we can pull in as well. Okay. If there's more pyruvate and the Krebs cycle can't keep up with the amount of pyruvate coming, then that pyruvate will get shuttled over into lactic acid. Okay. All right, what else do I have here? I put those on there and I did this. Okay. Let me talk about this and then I'm going to draw one thing and then we'll get you guys out of here. Okay. I like this because I think it's very practical. It's very practical. Again, I'm only going to ask you questions about this in a very general sense on the test. Okay. But what this is showing is the left side shows time. So from 1 to 3 seconds to like 2 hours. So this is if you exercise for a very short amount of time to a very long amount of time, where are we going to fall on the relative percentage of the energy that you use for that exercise that's going to come from anaerobic and aerobic metabolism? And it's pretty simple. Short-term exercise, most energy comes from anaerobic. Longer term, it almost exclusively comes from aerobic. Okay? You know, for most people, the 50-50 point is going to be somewhere between 2 and 5 minutes or thereabouts, kind of running. Okay? Now, this is influenced a little bit by exercise intensity. If I walk for 2 seconds, it's mostly going to be aerobic because it doesn't cost so much. But this is sort of if you go as fast as you can for 3 seconds or 10 seconds or 30 seconds or as fast as you can for 10 minutes or a half an hour or 120, this is kind of what the breakdown is going to be. Okay. Short-term energy demands for high intensity things comes from anaerobic. The one on the right matches up like actual events or tasks with what this is. So you can see, right, 100-meter dash, okay? Weightlifting, mostly anaerobic, almost entirely anaerobic. Gymnastics, 200-meter wrestling or 200-meter dash wrestling. And then there are these sports like hockey and fencing and basketball and volleyball and these things. They're very intermittent. It's a few seconds of high intensity, then you get to rest. So it's very anaerobic rest, very anaerobic rest. Okay. As we move our way down, right, we're going to do a 1,500-meter run. We're going to do an 800-meter swim where you just want to die and stop. Swimming is terrible. Okay. 10,000 meters, you're going to get out to things that are going to kind of be like this. I see. Okay. So just putting some things, like on a test question, I might ask kind of a very general thing, where the predominant amount of energy for a sport like sprinting comes from which pattern. The predominant energy that comes from doing walking a marathon comes from which pathway, things like that. Okay. All right, Freddie, your question.
Just because this does not make sense to me. When is the 1,500-meter run more aerobic than a mile run?
What?
The 1,500-meter run, when is it more aerobic than a mile run? Considering a mile run is 1,609 meters.
I don't know. This is a dumb American textbook. I never noticed that. There's a 1 mile run and a 1,500 meter run. The mile run is actually farther. Ah, okay, I don't know.
Especially because I run literally from 800 a mile and that's that.
I'm gonna be good to look at the faster.
But yeah, but why is it down when it's basically saying that?
Okay. I'm gonna give you guys an assignment, a take-home assignment. To turn in on Canvas by Monday. Where you're gonna have to sort of make a list and make a grid of some things, identifying what goes into the metabolic pathways, what comes out of the metabolic pathways, and what are some of the rate limiting steps, okay? I don't care if you work on it with a friend or a group. All I care about is that it gets turned in for Monday, and we'll play around with it. If you look at the next set of slides, there's no way we're getting through the whole thing on Monday. We'll only test you on what we get through on Monday, which will likely be talking about the idea of maximal aerobic capacity or VO2 max. We're not going to get into the fatigue side of things. We're not going to get to that on Monday. I put in the email, okay, that I sent to everybody. I put the potential questions on Canvas. I was going through looking at what was in the lecture kind of outline things. And I was like, I'll make a study guide, but I'm just gonna end up recreating what's on the lecture outline. So just use the lecture outlines for resistance training and aerobic training and metabolism and the VO2 stuff as your study guide. Okay? Those are gonna be ones. By Friday, please turn in the post-test 1 assessment. Okay? If I get it, I will give you 2 percentage points of an increase on your test. I think I get everybody's test grade. I think I got the math right on everything. Those are all. Okay. Well, there was something else I need to tell y'all. I can't think what it was. Anybody remember? I feel like it was something that one of y'all emailed me about. I'm like, hey, remind everybody about this. No? You good? Okay. All right. We'll see you guys next week. Have a good weekend. Make your choices. Yes. Let's figure out. We need to figure out what's involved. What there's not being on that. I didn't end up pushing it back. There's a reasonable chance it will get pushed back. We'll just have to. Yeah. You're gonna be gone. We will make an arrangement for you to be able to make that. Get back. So don't worry. Thank you.
You had it set up for like, all I have to do is set open then, like with my computer on the back. Yeah, so if it touches, and I know how to open it, you need to stare at it, so they do. Does that feel better?
Did I confuse everybody? Yes.
Yeah, I have a question.
Damn it. Okay, this is the hardest stuff that we do. Okay.
The bathtub thing would be theory, and then you saw about a drain, and I was like, we're at like a water park.
Okay, see, I knew I was trying to do something good and I messed it all up. Everybody was looking at me like, what the hell is he talking?
No, Peyton looked at me and I go, I'm getting water slide vibes, and she's like,
Okay.
oh, it's fine.
I said it back and I'm like, it's the morning, I'm thinking about a bath and it's this and you're not really like, and the water is what? And okay, that's fine.
Well, if your text is like, oh my gosh, there's this like one water park, I'm thinking like everyone went to in middle school, Blind Falls. Yeah, no, that's like literally what we started talking about, like I got really, not gonna lie. Thank you.
Of course.
Okay,
I don't know if it's because of like the way I've been taught in other classes about this whole process. But is it like, when you first start exercising, it's the creatine phosphate, and then that gets used up, and then it gets hyperphosphates, and then that gets used up, like.
Great question. Let me draw on the board. This will be helpful. And I can do this.
Because like on this thing, it's like this 10,000 meter run, it's